So the last part of this chapter is discussing what happens when we're at equilibrium and we change something about the reaction that knocks it out of equilibrium. So it causes the reaction to adjust. Okay, we're going to use Le Chatelier's principle, which tells us how a reaction is going to react to this event that causes the system to not be in equilibrium anymore. Okay, so when we're in equilibrium, remember the concentration or amounts of reactants and products is constant, meaning that this reaction is still going, but the conversion of reactants to products and the conversion of products to reactants is occurring at the same rate. So overall, we're not creating any more reactant or any more product. It's at this constant rate. Okay, so there are disturbances that can occur that can make that equilibrium adjust, and we're going to look at two of those. We're going to look at if we add or remove reactant or product when the system's at equilibrium or when the reaction's at equilibrium, or if we heat or cool the system to cause a temperature change. Okay, so when we add or remove a reactant, like we do in this example here. In this example, we're adding H2. When we add a reactant, now we have excess reactants, and the system's going to switch, the reaction is going to switch and move more reactant to product. Okay, so if we add a reactant, the reaction's going to shift. It's called shift to the right. It's going to make more product because we have more reactant to do that. Okay, if we remove reactant, like in this case, now we have less reactant than we had at equilibrium. The reaction is going to shift to the left to convert some of the product back to reactant to get us back to where the equilibrium was. Remember, because equilibrium is kind of that lowest energy place in the reaction, where the things prefer to exist at lowest energy. So if we're at equilibrium and we do something to shift it, the reaction is going to respond to that and either make more product or convert product to reactant. So if we add more reactant, the reaction is going to shift to convert some of that reactant to product. If we remove reactants, then the reaction is going to shift to convert product back to reactants to fill that gap. Okay. Same thing with product. If we add product, the reaction is going to shift to the left to reduce some of that product and convert it back to reactant. Or if we're at equilibrium and we remove product, then we've kind of got a low amount of product. The reaction will shift to the right to convert some reactant to product. Okay, basically we're trying to reduce what happened. If we add something, if we add product to reactant, the reactant is going to shift the other way to reduce the amount of reactant or product. So if we add reactants, the reaction is going to shift to the right to produce more product. If we add product, the reaction is going to shift to the left to produce more reactants. Okay. Then again, if we remove reactant, then some of the product is the reaction is going to shift to the left, and the product's going to go back to reactant. Or if we remove product, then the reaction is going to shift to the right to make more product. Okay. Then we have the situation if we heat or cool the system. Okay, and we're going to have to look at if the reaction was exothermic or endothermic to determine what's the response of the reaction. So for exothermic reactions, remember exothermic means energy is produced by the reaction, and During the reaction, energy is emitted, so it heats the surroundings. And during endothermic reactions, the reaction takes in energy from the surroundings to get to products. Okay, so during exothermic reactions, since heat is produced and emitted by the reaction, we put heat as a product. Okay, we do that so we can kind of keep track of things. We don't always write it there, but we're going to do it here to kind of be able to see things. So during exothermic reaction, if we add heat to all of it, so we have a reaction, adding heat means we're adding heat to both reactants and products. But if we add heat, that gives us an excess heat in the reactants, and the reaction is going to shift to the left and to reduce some of that, and results in creating more reactant. If you have an exothermic reaction and you remove heat, that makes the reaction shift to the right because we removed a product, and the reactants react to make more product. Okay, that's one way that if we want to get more product in a equilibrium reaction, we can adjust the temperature or the heat that we add to it, and we can get, in this case, it gets more product formed. Okay, for endothermic reactions, endothermic means we're adding heat to get the reaction to get to products. That means we're going to put heat as a reactant, and when we do that, we can see that if we add heat, that will shift the reaction to the right because now we have excess reactants, and it's going to convert more reactant to product for endothermic. And if we have an endothermic reaction and we remove heat, we cool the whole thing, the reaction is going to shift to the left to fill that gap, and the products are going to shift and make more reactant. Okay, whatever we're doing, the Chatelier is basically saying we're taking the stress off. We're trying to reduce the stress. So if we added something, we're trying to move away from that to kind of reduce it. If we've taken something away, we're trying to fill that gap. Whichever way the reaction has to shift to deal with it, that's how we're going to deal with it. Okay. Oh, so this basically all reactions in your body are equilibrium, and that allows for your body to shift which way the reaction goes depending on the situation. An example of that is the equilibrium that exists between hemoglobin and oxygen to form oxyhemoglobin. So hemoglobin is the molecule that carries oxygen in the red blood cells around the body. The hemoglobin picks up oxygen in the lungs and then travels around the body in the blood to deliver oxygen to the cells in your body. So when hemoglobin doesn't have oxygen in the lungs, it will pick up oxygen and produce oxyhemoglobin, which is hemoglobin that's got an oxygen molecule on it. Okay, so we can see that equilibrium reaction. So in the lungs, where you're breathing in oxygen, there's an excess oxygen. That's the place where there's more oxygen than anywhere else in your body. At that case, the reaction is going to shift to the right to produce oxyhemoglobin, right? So that's what we want to happen. In your lungs, hemoglobin comes back from delivering, an empty hemoglobin comes back from delivering oxygen to somewhere in your body. It gets to the lungs. It sees oxygen. So in the lungs, this reaction is going to shift way to the right to produce as much oxyhemoglobin as it can. Okay, now your body cells in your body need oxygen to do their reactions to either create energy or use energy. But when your body's working out or running or doing some strenuous activity, your muscles use oxygen faster. Okay, so in those places, the oxygen is low. That means the reaction shifts to adjust that. So as your oxyhemoglobin is traveling through the blood, when it hits places where there's low oxygen, like your muscles when you're doing a strenuous activity, the reaction will shift to the left and release oxygen into an area that's been depleted of oxygen. And then the hemoglobin goes back to the lungs, picks up more oxygen, and so on. Okay, so this equilibrium that exists between hemoglobin and oxyhemoglobin exists so that the places in your body that need oxygen will get delivered the oxygen faster, or more of it will be delivered there than other places that might not need it as much. All right, so that's the end of the Le Chatelier's principle, dealing with situations where you have a reaction equilibrium and there's some effect that something occurs to knock the reaction out of equilibrium, how the reaction adjusts to get back to equilibrium. All right.